All right, continuing on in Unit 1, we're going to discuss energy. So we've been talking about nuclear reactions, alpha and beta decay, and artificial transmutation. Now we're going to talk about energy of those reactions. Um, so there is a law, matter is neither created nor destroyed in chemical reactions. Same with energy. So this is chemical reactions, not nuclear reactions. We are talking about energy with regard to nuclear reactions right now. So Einstein determined that mass could be converted into energy, E equals mc squared. In nuclear reactions, and the key is nuclear reactions. This does not apply to just chemical reactions. A small amount of mass is lost and is converted to energy. So when only a small number of nuclei are under radioactive decay, it is a small amount of energy, but noticeable. Most radioactive materials feel slightly warm to the touch or glow, giving off light energy. When a large number of nuclei, such as 10 to the 24th or so, are made to react all at once, as in a nuclear weapon, an enormous amount of energy is released. So let's think about fluorine-19. So imagine breaking a fluorine-19 nucleus completely apart into the individual protons and neutrons. So I'm just going to go through this example. Don't be concerned that you have to do problems like this. It's more showing you the concept. So fluorine-19 has an atomic number of 9. So that means it has 9 protons, and the mass of 9 protons would be 9 times the mass carried out to many digits of a proton. 7.825 would give you 9.070425 atomic mass units. All right, 10 neutrons. 19 minus 9 would give you 10 neutrons. Is 10 times 1.008665. So the mass of a neutron is slightly different than a proton when you take it out to this many places, but we call it roughly 1 AMU. So you get 10.08665 atomic mass units. So when you add these up, that adds up to 19.15708 AMU. So the mass of the fluorine-19 nucleus is equal to 18.994 AMU. And when you take these two numbers and you subtract them, you get a difference of 0.1587 AMU, or when you convert that to grams, it would be 2.65 times 10 to the negative 25th grams. So when you plug this into E equals mc squared, so the c is the speed of light, and m is the mass, so we're talking about 2.65 times 10 to the negative 25th times 3 times 10 to the 8th. So this is grams, meters per second. This would be squared. Sorry if that's hard to read. Like I said, this is not a calculation that you're going to have to carry out. I'm more demonstrating the concept. So this would provide 5.66 times 10 to the negative 12th calories. And those are little calories. So if you take this further out, so a small amount of fluorine, about 19 grams, contains about 6.022 times 10 to the 23rd atoms. So 19 grams of fluorine would provide 3.41 times 10 to the 12th calories. So you get an idea. that if you had a nucleus undergoing nuclear decay, you would feel it. It would give off this energy, or you would see it glowing. Okay, so let's talk about fission and fusion. So these also are decay processes, or involve nuclear chemistry. So nuclear fission was discovered experimentally by Fermi and Segre. Further experiments to elucidate the nature of the reaction was carried out by Hahn, Frisch, and Meitner, who theorized that the nucleus was splitting into fragments. So it turns out that large nuclei are unstable. So when a neutron hits the nucleus, it can cause it to break down into many small pieces. So I always just simplify the definition of fission as the fragmenting of heavy nuclei to produce large amounts of energy. Okay, so if you want to think of this neutron as like a teeny tiny wrecking ball that goes into this heavy nucleus and starts chipping away at it, what happens is that it breaks it into barium and krypton, and then it also produces neutrons again. Well, these neutrons can react with another uranium nucleus, and so this process can go on and on and on. So this is a chain reaction. So in order to sustain this chain reaction, you have to have a certain amount of this uranium. So that's called the critical mass. So a sustained chain reaction was first carried out by Fermi at the University of Chicago. He determined the critical mass of uranium needed to maintain the chain reaction. So fission is what is used at nuclear power plants. And there aren't too many nuclear power plants in the United States. But in Europe, there are more nuclear power plants. So in a nuclear power plant, uranium-235 undergoes fission to produce energy. In the process of fission, neutrons are given off to continue the chain reaction. In the power plant, control rods made of graphite or cadmium are used to absorb neutrons. These control rods can be raised or lowered into the uranium so that the reaction is kept under control by allowing just enough neutrons to remain active so that the chain reaction can continue. The heat from the nuclear reactions is used to make steam, and the steam runs turbines to create electricity. The spent uranium, after reacting, is still radioactive and must be carefully disposed of. Due to the large amount of heat generated, cooling the reactor is extremely important. If the reactor is not cooled, the heat can cause the control rods to melt or burn. If the control rods are destroyed, the neutrons in the chain reaction are no longer absorbed and the uranium reacts very rapidly and explosively. This situation is called meltdown and is what occurred in Chernobyl. Okay. So I'm going to omit this. You don't need to worry about writing that out. What I do want you to know is what fission is. Okay, let me talk a little bit more about fission, nuclear weapons. So Leo Salazar realized that the chain reaction process would make possible the development of a weapon. The Manhattan Project was developed to design and build this weapon. After Fermi demonstrated the first chain reaction, a plant in Oak Ridge, Tennessee was built to separate uranium-235 from the more abundant uranium-238. The atomic bomb was designed and built at Los Alamos, New Mexico. by a team under the direction of J. Robert Oppenheimer. The test was successful and 2 atomic bombs were dropped on Hiroshima and Nagasaki, Japan. So that's fission. Fusion is also a nuclear process. So this is nuclear fusion, not a Ford fusion. Nuclear fusion is the joining of 2 small nuclei to make a larger one. This process requires high temperatures to cause the nuclei to join together. Large amounts of energy are released. So I'll put so both fission and fusion release a lot of energy. So in the sun, hydrogen atoms are fused together to make a helium atom. So this is hydrogen 1, this is hydrogen 2. They fuse together to form helium 3. The release of energy from this process provides heat and light for our planet. Note that this cannot occur as a chain reaction. It also requires a large amount of energy to initiate the reaction, such as the very high temperatures in the sun. It is very difficult to reproduce this process on Earth because of the high temperature needed to cause the fusion to occur. It has been done by pointing several high-energy lasers at a small pellet containing the hydrogen reactants. It required more energy to start the reaction than it gave off, so it is not economically feasible. It is of interest because the starting material, hydrogen, is very cheap and readily available, and the end product, helium, is non-polluting. And the hydrogen bomb, a small uranium bomb, is used to provide energy to initiate the fusion reaction. So I'll put H-bomb, difficult to reproduce on Earth. So in some movies, they talk about cold fusion, and it is highly unlikely that you cannot carry out cold fusion. It requires the high temperatures. Okay, so lastly, we're going to talk about consequences of nuclear explosions. So after a nuclear explosion, the radioactive particles can rain down on Earth over a large distance and for a long period of time. This is called fallout. So radioactive particles rain down on Earth over a large distance and long period of time. Some of these radioactive particles are similar in chemistry to elements needed by the human body, so the radioactive particles can become incorporated into the body and lead to cancer. Which leads us to nuclear winter. A scientist named John Birx theorized that the detonation of nuclear weapons would create a large amount of smoke and dust in the atmosphere. The dust would be carried up to high levels of the atmosphere, much as like the dust from volcanic explosions is, but would be thick enough to significantly block out light from the sun. So, smoke and dust from nuclear weapons would block sun. So if there's less sunlight, the surface of the earth would experience significant cooling, and many plants and animals would not be able to survive. Plants and animals die. So we talked about fission, fusion, and their applications, and also the consequences of nuclear explosions. So we'll stop here for now and come back, and we have a little bit left in Unit 1.